Okay, good morning. Welcome to Geometry Project 8, which is going to be a discussion of section 1.8 of Geometry Revisited, called the 9-point circle. Much like yesterday, this section is insane, but I'll give the same warning or a little disclaimer that I gave at the beginning of the video yesterday. I really gave up on this section when I was in high school trying to make it through this book because it just looked too complicated. Take a look at the picture. But it turns out, I mean, the funny thing about this section in the book is it's probably about 1 page of text, 2 drawings, and then a couple exercises. So in total it takes up about 2 pages. It's just dense. And there's just only a couple of ideas. So it's not super difficult if you stay with it to see this. What we are going to prove in this section is the feet of the altitudes of a triangle. So D from AD, F and E, the midpoints of the 3 sides, A prime, B prime, and C prime, and the midpoints of the line segments connecting the 3 vertices to the orthocenter. So on the altitudes, you take the intersection point and you go halfway back to the vertices. So that's K, here's the intersection point halfway back to the vertice M and L. Those 9 points, the feet of the altitudes, the midpoints of the sides, and the halfway point from the vertex down to the intersection of the altitudes, those 9 points all lie in a circle. That circle is cleverly named the 9-point circle. And I know what you're thinking. This is obvious, right? But bear with me. We'll spend a little bit of time going through this, and just for fun, actually, you know what? I'll draw the circle at the end because this drawing's already complicated enough as it is. But before we get started, one funny thing that you can see the authors of the book have a little bit of a sense of humor, because the first sentence begins, "To make things a bit easier," and then they draw this drawing. Alright, so what do we need to take a look at? The very first thing we're going to take a look at in the picture here is this thing that looks like a rectangle, and we are going to actually prove that it's a rectangle. B prime, M, L, and C prime. And let me switch to a different board just to make an easier picture. Okay, here's my hopefully slightly easier picture. I've got triangle ABC. I've drawn the altitudes intersecting at point H, and I've drawn B prime and C prime. Those are the midpoints of side AC and AB. And I've drawn L and M, although I've not drawn them very well. Where's my marker go? Those are the midpoints of the segments CH and BH. So C prime and B prime are the midpoints of the sides, and M and L are the midpoints of H and HC and HB. And what we want to prove is that C prime, B prime, M, L, C prime is a rectangle. Well, let's take a crack at it. The first thing to notice is a property about C prime, B prime. These are the midpoints of the sides, and that means that AC prime is half of AB, AB prime is half of AC, and we have the triangles ABC and AC prime B prime have the same central angle. So these triangles are similar, and since AC prime is parallel to AB because they lie on the same line, and AB prime is parallel to AC, again they lie on the same line, that means C prime B prime is parallel to BC. Okay? So we just learned a nice little feature about C prime B prime. It's parallel to BC. Similarly, the exact same argument, but instead using the triangle BHC instead of ABC. So we have the triangle BHC and the triangle LHM. The exact same argument shows that LM is parallel to BC. But if LM is parallel to BC and C prime B prime is parallel to BC, these two things are parallel to each other. Okay, well that's nice to know. So next we need to figure out about CL and B prime M. And what we're going to look at now is, again, the exact same argument, but let me draw a different triangle. Let me see if I can draw this one in purple. We're going to look at the triangle AHB and the triangle BC'L. So, in this triangle, BC prime is half of BA, because that's the midpoint. BL is half of BH, and these two triangles, BC'L and BAH, have the same central angle. So once again, they're similar. And now, since BC prime is parallel to BA and BL is parallel to BH, we know that not only are the triangles similar, their sides are parallel, and that means C'L is parallel to AH. The exact same argument, but with these triangles over here, AHC and B'Mc, shows that B'M is parallel to AH. So we have a nice little thing. C prime, B prime, and LM are parallel to BC. Okay, so C prime L and B prime M are parallel to AH. C prime, B prime, and LM are parallel to BC. But here's the thing. AD, well, AH is part of HD, which by definition was an altitude, and that means AD is perpendicular to BC, and because of all the parallel lines here, that means those two are perpendicular, these two are perpendicular, those two are perpendicular, and those two are perpendicular. So the book explains this in 2 sentences, and I wanted to spend 5 minutes going through to make sure you understood how that worked, because they don't give a lot of explanation for why they're parallel and why they're perpendicular. You have to connect the dots. I mean, they don't say anything wrong, they just do it a little too quickly. So here you go. So this is the critical observation. So we know that C prime, B prime, LM is a rectangle. Okay, so back to our original picture. So where is the rectangle here? C prime, B prime, M, L, C. That's a rectangle. The exact same set of arguments shows you that A prime M, K, C prime A is a rectangle. The only difference in the argument is instead of using the vertex A, you're going to use the vertex B. And then see if you can see the third rectangle. What's it going to be? Can you see it? Anyway, the other rectangle is right here. A prime, B prime, K, L, A prime. Maybe I'll draw them in different colors so they stand out a little more. And we'll draw this one in green. So amazingly, we've got inside of this crazy picture, we actually have 3 rectangles. And one important thing to notice about this rectangle, the rectangle A prime, M, K, C prime, I'm just going to pick its diagonal AK. And let's look at what we can learn about the diagonal A prime K. Well, A prime MK is a right angle. A prime B prime K is a right angle. I'm going to skip E for a second. A prime C prime K is a rectangle. I'm going to skip F. A prime L K is a right angle. And I'm not going to skip D. The A prime D K is a right angle by definition. So you only have to figure out now why A prime EK is a right angle and A prime FK is a right angle. I'm going to skip that and leave it to you to see if you can figure out why this is a right angle here. Can't do everything, but why is it important that those are all right angles? Well, when you have a right angle triangle, it's inscribed in a circle with, in this case, A prime K being a diameter. And so what this shows, once you convince yourself that A prime FK is a right angle and A prime EK is a right angle, what that shows you is you can go all the way around this and everything's on the same circle. A hint on how to figure out they're on the circle, which means just draw a different diagonal. In this case it's going to be L. I think LB is a good one to draw. LB prime, that's going to show you that E's on the circle. So that's fascinating. It's just absolutely fascinating that all 9 of those points can be on the same circle. It turns out not to be all that difficult. You find these crazy little rectangles that live inside of there, and you just use the feature that a right triangle inscribed in a circle has the hypotenuse equal to the diameter. The last thing I want to point out is, well, sorry, there's 2 last things I want to point out. One is that the triangle that's hard to see in here, the medial triangle with feet A prime, C prime, B prime, is half the size of the big triangle ABC. It's because it's the medial triangle. And that means that the radius of the 9-point circle, which is the circumcircle of A prime, C, B prime, C prime, is half the radius of the big circle. So that's not too surprising that the radiuses should be related to each other. And now we just need to show the last thing. Where's the center of this circle? Well, we have 2 triangles in here, and I'm basically out of colors. Let me draw them in blue. We have triangles KLM, and we have triangles C prime, B prime, A. I don't know if you can even see that anymore. This is so complicated. But it turns out those 2 triangles are similar. In fact, they're congruent because their sides are equal to half the sides of the original triangle. Now here's an incredibly clever mathematical argument. You remember when we talked about the medial triangle, A prime, C prime, B prime, we said that the orthocenter of the big circle ABC, big triangle ABC, is the same as the circumcenter is the same as the orthocenter of A prime, B prime, C prime. And the reason is the perpendicular bisectors of the sides of the big triangle just happen to be the altitudes of the medial triangle. So the orthocenter of A prime, B prime, C prime is the same as the circumcenter of the circle ABC. Now, the orthocenter of KLM, which is the triangle that you get by taking the distance from H to A dividing by 2, H to B dividing by 2, and H to C dividing by 2. Now remember, A coming down to H is an altitude of the original triangle. And so when I do this triangle KLM, the altitudes are actually the same. So the orthocenter of KLM is the same as the orthocenter of ABC. Well, it turns out these 2 triangles are congruent. And what you can do is you remember we have a circle that goes around like, sorry, that's not going to be so great of a drawing. But we have this circle that goes around, and we can rotate the circle 180 degrees. Just go, shoop. And the triangle A prime, B prime, C prime goes on to the triangle KLM, and then H and O just switch places. But everything else is the same. You're just rotating the circle around its center, and if H and O switch places when you rotate it 180 degrees, that means the center of the circle is right in the middle. Now, I know that's a complicated argument, but it's a very, very clever mathematical argument to figure out where the center of the 9-point circle is. It's right in the middle of the orthocenter of ABC and the circumcenter of ABC, and it lies on the Euler line. That's why we talked about the Euler line yesterday. And trying to calculate where this is would be crazy, but the symmetry argument of just turning the circle 180 degrees gives a very clever proof of where that lies. So let me go back to the beginning and say, when I was in high school, this section seemed intimidating and way too complicated. But in fact, the ideas in this section, other than calculating where the center of that circle is, which is indeed difficult, the ideas are just about parallel lines and inscribing right triangles in a circle. It's really not that. Each individual step isn't all that difficult. Putting them together is hard. And you have this clever thing, the 9-point circle. Thanks for watching.